Thank you, dear co-organizer. Yes, so I want to maybe try to give a talk which partly uses slide and partly the board. So we will see how that goes. So I talk about joint work with Enrico Brehm. And I want to explain how one can go from a continuum two-dimensional conformal field theory to a lattice model. And it'll go, I mean, the lattice model is very easy to define. That's what happens in step 2 here. I want to do the easing model as an example because it's our Rosetta Stone of comparing different ways you have of looking at these theories. And then I want to discuss something I call the stability condition, which might be a criterion which decides whether your lattice model lies in the correct universality class. Okay, and with that, I will briefly try if I can blank the projector. Ta-da, that worked. And okay, I have to do many things. I have to switch that light back on, I think. No. Yes. Okay. So let's see, what are we trying to do? What are we trying to do? Usually, if you have a statistical lattice model, then one thing you're interested in is how do correlators of this lattice model behave at large length scales. And you would try to extract some kind of universal behavior, which is often called the universality class of the lattice model. And you go from here to here by looking at the long-range behavior, because that tells you anyway everything you can measure about the model. Oftentimes these universality classes are described by two-dimensional conformal field theories. So I will take this to be a two-dimensional conformal field theory, and I will work in the entire talk, I'll work Euclidean. So I will not talk about spin systems and Hamiltonians, but about statistical models. Now, that's the usual direction. In a way, it's the interesting direction because you want to learn about this model and you can do it via this tool. But maybe from a theoretical point of view, it might be interesting to ask if you can understand a conformal field theory, does it happen as a universality class of some lattice model? And is there maybe a way to come up with a lattice model which has a chance to reproduce the 2D CFT? So that's something I want to think about. I will not be able to prove anything, but I want to give a construction which can maybe be a section of this, right? So the idea is to build a lattice model, or more correctly, a family of lattice model, which maybe has a chance that if you look back at its long-range behavior, recovers the original CFT. And I want to do this in slightly with an additional ingredient. So in this 2D CFT, I want to fix a topological symmetry, by which I mean I want to fix a fusion category F of topological line defects in the 2D CFT. And this construction will be designed in such a way that it preserves the symmetry exactly. So it'll automatically produce a family of a lattice model which also has topological symmetry F. So these symmetries are then realized exactly on the lattice as topological defects. So that's the aim. Okay, and then with that, I can go and so the actual construction here is very easy, and we will think a little bit about its.
So it's RCFT.
Because then you want to go RCFT, but no, we can do slightly better. In practice, the answer is yes. I am doing RCFT.
Okay, yeah, that was going to be my
response. But really, I need what I want is that the symmetry which is preserved is finite. So that sort of enters the construction in more detail. But I mean, you could take a non-rational free boson and you can still find finite symmetries in there, right? So you could run it for that in principle. I didn't try, but.
Well, yeah, it's also thinking, nobody's limited what happens when, if there's just an infinite number of these defects,
right.
It's not a fusion category.
Right, and so this construction does not work instantly in that case. You will see the obvious place where I will sum over the simple objects here. Yeah, you go like that. It could be that there's some sort of integral formulation where you can, if you try to do, but yeah. So that sounds like a question which is better asked when I tell a little bit about the construction. No? Okay, go, ask.
Then map to CFT, and supposing that when you take the arrow in the other direction, you will end up with some perhaps more strange looking lattice models.
Perhaps.
Is there a way to relate those to the ones that change the others?
And so indeed so the arrow first produces something with an infinite number of states. I'll then brutally truncate it, thereby lose all control, and then I wave my hands to say that that model still has a chance to reproduce. Okay. So I wanted to switch that back on, but that didn't. Yes, so this lattice model has the same topological defects which I decided to preserve. So I can point. Well, I'll give you a local lattice model, and then you can put it on any configuration you want, right? So I think, let me present the model, and maybe some of these questions answer themselves. So as I say, this model very easy. Okay, this needs the other one. So here's what we will do. So we will take our input, which is a two-dimensional conformal field theory, which at some places I will make some implicit assumptions on the theory, and they are all covered if I ask the theory to be unitary and to have a to be compact in the sense that it has a discrete spectrum. Now you can relax these assumptions, but then you have to be careful at various places. And I don't want to be, so think of this as a unitary discrete spectrum theory. And I point at a fusion category of topological symmetries. I insist that these are not all the topological symmetries of the series, which typically are infinite. But I want to point at a specific fusion category in there, and I want a construction which preserves this. Okay. So what will we do? We take a surface on which the CFT is defined. So here's a torus with a funny modulus. And then in the first step, I will cut a number of holes into the torus. They will all have some radius r, and their centers will be placed at some distance d. And I place a conformal boundary condition on these holes. Always the same conformal boundary condition. Then that's still a surface. I can evaluate my conformal field theory on. And so we will continue in a little bit, but I first want to point out that once you do this, there is an immediate problem with the idea of preserving the topological symmetry, which is that if you have a topological defect x, well, you can, because it's topological, freely deform it on your surface, but once you have punched all the holes into it, you cannot. A priori you cannot. It's sort of not clear why passing the defect above the hole and below the hole should give the same answer. Right, and so that's maybe the one calculation I do in a little bit more detail, is to explain that if you choose your conformal boundary condition cleverly, then this property remains true. So the hole can be made invisible to all defects in this fusion category F. Okay, I will switch this off and do this computation. Okay, so that's what we want to do. We want to take a defect past one of these. Yeah. I would say in a one-dimensional boundary, probably. You could do that too. So I'm saying that's the simplest setting. So the simplest setting is that the holes are placed on an equilateral triangular lattice, and they are all holes of the same radius. But you don't have to do any of this. So you could do other lattices, you could do different radii, you could do different boundary conditions. I'm just saying, so that's sort of the easiest setting. Well, we will get there. We will get there. So this theory is a conformal field theory, right? So it's not topological. And the position of the holes matters, right? So once you put a conformal hole, if you move it, it changes the value, it changes the expectation value. So the only thing at topological at the moment is the line defect over here, and over here we have to do some work. And maybe as a teaser, the way I will discretize it is I'll sort of do open string factorization. So I'll do intermediate sums over the interval here to take it apart. But we will get there. Okay. More questions at this point? Okay. Erase this maybe with an eraser. Did anybody see an eraser? Oh, here. Okay, there's also one. Okay, I will use the one on the ground. Oh, I didn't see that one. Thank you very much. Okay, and what I want to build before the boundary is something I would call a cloaking defect. And so what I want to achieve is that if I think of having some patch of my two-dimensional surface, and then here's some area about which I don't know anything, so it could be maybe have some homogeneous in there or whatever, or some boundaries, I don't care. So there's some anything region, maybe other field insertions, and I want to achieve that if I have my defect X, which passes above this area, I want to be able to deform it so that it passes below the area. And the way I will do this is I will, probably the other way around, I will insert a sum over sum over simple objects in F. That will be my notation for the sum over simple objects in F. And so the category theory people are now not allowed to complain that what it has infinitely many objects. But so it's a fusion category, so it has finitely many simples, so that's a finite sum. It's also a spherical fusion category, so I can talk about dimensions. And I take the quantum dimension of the simple object A, and I take this sum of expectation values. And so pretty much anybody who's done a three-dimensional TFT from this Resticken to Rayev perspective has seen this sum, because that's the surgery color or the Kirby color you use in verifying that your not invariant satisfies the Kirby moves. And the same calculation which you use to check that will help you to transport that defect past that circle. So let's try. So I first look at this area, and I expand these two parallel topological defects in a sum over simple defects. So I'll still have the sum A and F dim A. But now I want to, and then I will draw this picture once more, but the rest of the computation I'll do by wiping. So here's my anything area. Then I've got this circle, A. But then I want to use a sum over intermediate simple objects here. So I've got X. Then here I have B, and I sum over B and F. And then maybe I've got some basis and dual basis here, and I sum over that too. Right, so that's an identity that holds locally in this area. Okay. Then I will topologically deform the situation, because these are topological fields, these are topological defects, and I will take this point and deform it down here. Okay, so let's get the arrows right, and then in the middle there's still an A, and this one I deform in the same fashion. Right, and so this was phi, this was phi bar. Yeah, this. And now there's the one point in this computation where I have to sit down and do an actual little computation. And I leave that as an exercise, which is that if you do this sum with these weights, then the answer you get is the sum now. So the sum over A goes away. That will be a sum over intermediate states. You can check that these funny bend versions of phi and phi bar are still a dual basis pair. That's the computation up to dimension factors, and they precisely correct this dim A. So I claim, exercise, that this now is precisely equal to dim B. And then my picture with the something here. Now the sum here goes over B, but the defect X now passes on the bottom. Okay, so that's well, that's the one computation which explains why that works. Yeah. How can you even see that? Okay. Sorry, say that again more slowly. So I'm saying it doesn't really matter. Whatever is in the middle here, that's true. So there could be nothing, right? So then it's true trivially because you can just collapse it away. But what we will later do is to just put a boundary circle here. That's in fact what I will do next. Okay, more questions or comments? Now that's a weighted sum over configurations, and I want to turn it into a single boundary condition. That's not quite possible, but I can, or a single defect, but I can turn it into a defect with an insertion of a point field. So I can define finally my cloaking defect, which surrounds anything. Let's call it gamma hat. It depends on your fusion category. We will see, so I want to define this first of all, so gamma hat F. I want to be a direct sum over the simples in FA, right? So then the fact that this is a superposition will produce the sum over A, will not yet produce these factors, and so we stupidly insert a topological point operator, delta F, which maybe is some normalization constant, which you can fix. And then again, you sum over the simples in F, and you take this weight, dim A, and then you make it artificially sit on that component by multiplying with the identity operator on the summand A, right? And so if you expand this out, you get precisely the sum. So this specific object with this point operator has the property that you can take topological defects from F past it. Okay. This is looking very much like a stringlet, but it lives inside the conformal field theory. So, right. So that's good. So that's the other place where you have seen these operators. If you do stringnets, then one way to compute a stringnet on a complicated surface is to introduce one hole and then map it to a Hom space and then get rid of this hole with this projector. So that's another. So you may have also seen that in stringnets. So indeed, if you choose this normalization appropriately, this acts as a projector. If you do it twice, you just get this defect back. Okay. The more. So the phi lives. So these phis are a basis of a Hom space in F, and it goes from what, X tensor A. And phi bar, sorry, what? Phi is this one, and it goes from XA into B, and then the phi bar is just a dual basis with respect to my favorite pairing, which is not the pairing everybody else uses for some strange reason. But it should be everybody's pairing. Okay, so that's a defect, but we wanted to take. So you mean right, so you could put your favorite field in here, and that's still true. And it'll be true, so depending on, so in the example we will see later, it'll be true for the stupid reason that it'll project that to the overlap with the vacuum. But it could, and it will therefore typically be 0. But for other choices of F, so for example, well, we can discuss the examples afterwards. Okay, more questions or comments? Right. So this defect is a superposition of elementary topological defects with the label A. Each of these carries a copy of the identity operator. And so I can write down a weight 0 field on this, a topological field on this, by taking some superposition of the identity operators of the various components, and I say I take this. And so that's the point field insertion on here, which is topological. And it's chosen so that it reproduces these weights if you expand it out. So you need this, otherwise you can't take. So the property that you can take a defect past this fails if you don't have this operator. Okay. Yeah, but it doesn't matter, right? So actually what will happen later, but I will skip it because it's too technical, is I will even split this into several, take some higher root of this and split it into several places so that it's more symmetric. So it can be anywhere, indeed. So it's topological, so you can... Okay. Goodie. So now we want to turn this into a boundary. So clearly what we will do is we will put a boundary circle here, and we will put some conformal boundary condition. I think I wanted to call this U. And then, because this is a topological defect, we can just shrink it onto the boundary, and then we get a new boundary condition, gamma. So I leave out for the boundary condition gets no hat. I should remember the U, but I will drop that from the notation in the future. And then I get this boundary. And this boundary now has, by construction, the property that if I have an X in F, then I can pass it below that boundary, and these two are identical. That's an identity locally in correlators. Okay. Sorry, I need the field, so I need this delta here. And because I don't always want to write the delta, I will include it in the notation here. And because I'm lazy, I'll also not always write this in brackets delta here. So by this gamma will mean the boundary condition, so the cloaking boundary condition which hides the whole. Okay. So let me go back to the projector. Well, I'm saying that's the boundary condition I choose. So I'm trying to present a construction where I start from these two pieces of data and produce for you a family of lattice models. And one step is to take the surface and cut these holes into it, and equipping the holes with a specific boundary condition. Right, and so you have to make a choice there too. So I should have included in the notation. So that's another parameter you have, which I should have included there. But later in the examples, there'll be sort of Virasoro minimal models, and I will take sort of the identity Cardi boundary state there. So true. I should probably, for completeness, have said you also pick a preferred boundary, conformal boundary condition of C. So at the moment, if you put different boundary conditions to the circle, you get different answers, right? And I haven't told you the lattice model yet, but you will see the state space of the model depends on this boundary condition, and I want to choose this specific cloaking boundary condition. That's what I want to do. So this sum with the weight.
A single circle, I can impose a condition that preserves a single Virasoro.
Right.
Call that a conformal boundary condition.
Right.
We have this lattice, there's a lattice spacing that breaks the
But at the moment, so that's still in the so at the moment there's a lattice, but that's still a conformal field theory, right? There's a conformal field theory on a complicated surface. It's a surface which has many holes, and each of them has a conformal boundary condition. So at the moment, I'm not yet at the lattice model. I can evaluate the conformal field theory on that surface. Scale, well. It's scale invariance in the appropriate sense, right? So if you map this to another surface by a conformal mapping, which deforms the holes in some way, well, that's still an identity. But it's true that if this is modular invariant, it's no longer modular invariant, right? Because the holes will break that. But my point is, I can evaluate the conformal field theory on that configuration. It makes sense. That's a valid input for the CFD. Yeah, but that's for simplicity, but yeah. Yes, yes. I'm not saying the lattice model will be exactly conformal because it was lattice. But anyway, so that's what I said. I have to do the special boundary condition. I have to put these point operators, but then I can make this work. I can take the defect past the hole. I will in the future not write these anymore, but they're always there. And so what's the next step? Now we want to build our lattice model. As we just said, that's very easy. So we take our surface, and I've marked some intervals on the surface, and I want to cut the surface along these intervals, and in these places insert a sum over an orthogonal basis of intermediate states. And so that's what is happening here, right? So I'm cutting this into many triangles with clipped edges. So the green, that's where the conformal boundary condition is, and the red one, that's where the states sit I'm summing over. And so the kappas here are the orthonormal basis of boundary states or states on the interval, and I'm summing over one set of basis vectors for each of these intervals, right? And so that's an identity in CFT. So that's just equal because CFT satisfies this factorization of correlators. So I've written my complicated correlator as a big sum of disk correlators. Okay? And now this big sum of disk correlators I want to interpret as a lattice model. So maybe I can write this. I have to make a little bit of space maybe.
There's no sum of the delta. It doesn't matter. The delta you drew in the previous slide.
Oh, the delta is fixed once and for all. So I've it doesn't. Right. So that's the technical detail, but you can clobber me with it. So let's see. So
I'm trying to understand global questions.
So what I'm.
How are you breaking conformal?
Oh.
What fits the guard?
Well, at the moment it's still a conformal field theory, right? But it doesn't have the conformal symmetry of the original surface because you've introduced all the holes.
Yeah.
Right.
And the delta is
And the but so in the construction in practice, what I do is I sort of spread the sixth root of delta symmetrically around the circle so that each triangle gets sort of a symmetric contribution of it, but it's
that's how you're getting the symmetry of the six-fold symmetry.
And
I mean, because that does
have threefold.
rotational symmetry.
So I'd say it has a threefold symmetry, but yeah.
Yeah, sorry. Threefold. So can we talk a little bit more? What's the sum of this KJ?
Yeah.
Like the solution of the identity?
Yeah. And it's infinite, right? So it's
What is it, like a dot?
like right. So in CFT, you would have some representation of a single copy of the Virasoro algebra sitting there on this interval. It's infinite, and with respect to some orthogonality condition, which I don't tell you, you pick an orthonormal basis, and then you sum over that.
So I'm not used to this. So this is something living on the whole red line.
Well, that's I mean, so then what I will do is I will say I use the state field correspondence. So if I have a state kappa I here, well, I can also represent this by some corresponding field insertion on the circle where this is now my boundary condition gamma gamma, yes, and I will just glue these circles to all these triangles. So then what the triangle becomes, so I start, so that I will need anyway, so let me write that. So I'll start with my triangle with clipped off edges, like this, right? And so here's my boundary condition, and here are states, and I want to use standard conformal field theory technique, so I'll glue these half disks here, and then I sort of have kappa I, kappa j, kappa k here, and so then you can uniformize this just to a disk with 3 insertions, and then this you can evaluate by that it doesn't even, that's completely fixed by conformal invariance up to a number. Well, no, you can do this with 15 insertions, and you get a disk with 15 insertions, and it's just a pain because it's not fixed by conformal invariance anymore. So, well, I could have done that lattice, and then unluckily I would have used one with 4. So this also works. It's just harder to evaluate what the weight is. In the sense,
imagine I pick zero would be a valid boundary.
Yeah, then you construct a zero lattice model.
If I cannot, the argument you just made, I cannot do because I cannot
Right.
take the sum.
Well, I can still, because if this is the zero boundary, then the state space is empty and the field space is empty, and the zero space still isomorphic to the zero space, so formally fine. But I mean, I is, you know, if you treat these boundaries as objects in a category which has direct sums, well, then there is the zero object. I would feel this technical discussion about what the zero boundary does, we can fight over afterwards. But I think I would treat this as an axiom in CFT that you have the state. So, but what I mean by a state across the interval, by definition, is what this generates. Yeah. Yeah. So that's sort of hidden in here, right? So. Yeah. So this is the sum. So as the boundary, so there will be this point insertion somewhere, but just the boundary condition is the superposition where I sum over A and F, and then I act with A on U. So if I use sort of module category notation, then that's what that is. No, but I will later say something about how different choices of F lead to different lattice models. But your question also very interesting, but it's on the to-do list. So this, so to explain the lattice model, so I will erase this bit here with the state field correspondence. So this is a local bit of my lattice model. Then the degrees of freedom live on the edges in this formulation. I later transfer them to the faces, but at the moment they live on the edges. And they are labeled by the spaces kappa I, right? So at the moment that's infinite, and the weights live at the vertices. So here there will be some weight which I call TF, triangle weight, for a hole of radius r, and it really also depends on the choice of f and delta and u, but I'll not write all that. And so I take my three basis vectors. And this number is defined to be the value of this disk correlator, right? And so you may wonder, once you've uniformized this, where did the R dependence go? But the R dependence hides in the uniformization map, and so it hides in the local coordinates. The local coordinates of these field insertions are very complicated, and they depend trivially on the radius. So this correlator does still depend on the initial radius of these holes. Okay. So that's the lattice model. It is not, as I think you said, not very pretty at the moment, because it's a bit weird because it has infinitely many degrees on each edge. I later truncate it, but I want to think a little bit about this general model first. So let's first think about what the topological symmetry does. So we have, if we insert a topological line in the CFT, then it just gives me a new kind of triangular plaquette, which would be the one I've shown here. It's just one of these clipped triangles with a topological defect running through it. And if I map that back to the disk, it would be something like where a topological defect runs from one of these insertions to another one of these insertions. And again, you can evaluate this in conformal field theory. It'll give you some number, and that'll be the weights for plaquettes which contain these topological defects. And on the lattice, on the corresponding lattice model, you could represent it like this. So the topological line runs on the edges of the lattice, and just the weights and the state spaces are modified where this purple defect runs. And then, but because these are all equalities, right? So we just rewrote a CFT expression. These are equalities. So up there, we had the identity that we can move the defect past the hole. Well, then that identity holds exactly on the lattice. Okay. So far, so good. Yeah. so the boundary condition, so you mean this u, the little u I started with, or the gamma, or so? Yeah, so that is contained in, so that's the basis of the state space on an interval of the CFT, which has this boundary condition on either side, right? So if you choose different boundary condition, you get different state space, therefore you get sort of different bases, and then it also enters the weights because it will affect what the value on the disk is with these boundary conditions. Right, so the basis of this state space, infinite. It's a CFT representation, right? So that's.
We have to take the full. Okay.
And I will soon only take the primary, but. Okay. They are just not there anymore. So typically they will be broken on the lattice model. So if I, yeah, and so these would so if this model works and it flows to the same CFT, then these would be recovered. So you know that's kind of expected, right? It's a universality class, so it's a universality class for different many local models, and the universality class has to kind of have the union of all the topological symmetries you find in your lattice realization. So it's sort of not. Well, that's also an interesting topic, which I so as I said, so this is related to a number of constructions which appeared. So there are models Fentley and al, so Paul and al have constructed, and Frank and al have constructed, and I want to discuss how these are related. And in your models, you do get these families, these integrable and translation invariant families of defects, right? So one could ask. And so I don't know how to do that here, is what I'm saying. So I wouldn't say a priori it's totally impossible, but I don't know how to do that. Yes. Yes. Well, now you can do this. You can well, once I've truncated it, you can put it on your computer, right? And it'll give you a number. Right. So you can, I mean, that's up to you, right? So now you can put it on a torus and you compute the partition function, you put it on a disk, you put whatever geometry, and then you compute you can compute correlators, right? You could put, so there's a natural way to include observables by placing fields in the middle of these triangles. And at the moment I cannot, but soon I can because I'll truncate it. Ah, but no Hamiltonian. Okay. So it's a statistical lattice model, so no Hamiltonian. It's a different question to which I also don't know the answer, is can I construct a spin chain by some related thing with a Hamiltonian, which sort of is like the spin chain analog of this, and I don't know the answer to that. Because what goes wrong, right? So clearly if you have the lattice model, you can construct the row-to-row transfer matrix, then you can take its logarithm, and it'll not be local typically, right? So I don't know how to do that bit. Say that again more loudly. So how do you? So you're allowed to modify the boundary condition by sort of modifying the seed boundary condition U, and by modifying the symmetry F you pick. And I didn't investigate this systematically. A priori, they always give you different answers. I don't know what that means. What? So, what? Right? So a priori, only the entire sum is. So where's my sum gone? Right. So the U, you have to fuse this with U, right? but so in one example, which I didn't look at, is the easing example, where I would take 1 plus epsilon and sigma, and then I would just generate 2 copies of sigma, but 1 copy would also work. That's something we didn't look into. So there are some, so this works, but other things may also work. It's a projector. So it's a many-to-one map. Righto. Now I forgot what I wanted to say next. I think I want to do an exam. No, I want to relate. So before I truncate, I want to do relate this expression back to CFT. Maybe I try to, I erase this and keep this on for reference, but we'll switch it off again later. Okay. Shouldn't have it erased. So we had these weights which we assign to. So we have a weight which, or maybe T, I call them TR, and they depended on these kappa I, kappa J, kappa K, and they basically were the value of this clipped-off triangle where the states are kappa I, kappa J, kappa K. And the boundary condition is always gamma, and secretly there's also this field point, but I will skip it. And so what's the partition function of that model? So let's say we do Z, R is the partition function of that lattice model for a particular choice of radius. And we would write this, and it depends on many more things, on the CFT, on U, on F, but let me write it like this. And so we have to sum over all lattice configurations. So these are all configurations of states on the edges. So I will write this as a map which goes from the edges to the base. Let me call this map E, B, well, I'll just not give it a name. Edges to bases, right? So that's the sum over local configurations in my lattice model. For each configuration, for each such assignment, I take the product over all of these weights. And the product I have to take over vertices. So let me write this as vertices V. And then for each vertex, I get a weight which depends on the state on the 3 adjacent edges. So I'll write this as kappa V1, kappa V2, kappa V3, where V1, V2, V3, maybe I should, maybe I give it a name. So I don't know, let's call it phi, and then it would be phi of V1, phi of V2, and phi of V, maybe like this. So V1, V2, V3 denotes these 3 adjacent edges, and then phi evaluated there denotes the basis element which is assigned to that edge. And so that's the partition function of the lattice model, right? Now this is still, at this point, because we didn't truncate, exactly equal to the CFT expression up there. So therefore, we can do the following, which is not what we want in a lattice model. We would eventually want to take some large distance limit, but at least to point this out, a thing we can do is we can take the limit of the whole radius going to 0, right? And it turns out you can compute what that is in the CFT. It turns out that if you multiply this with some constant, which I will not explain, some constant, then you take the radius, you take this to the plus c over 6 times the number of holes. So if you shrink the whole radius to 0, the partition function is singular. The singularity is r to the minus c over 6. That comes from the conformal anomaly. And you can compensate that. And so, and if you do this, then the leading term is just the vacuum state of the CFT. So that's the no hole. Hole is gone in this limit. So that's exactly equal to the CFT partition function, right? So, so that's a stupid way of saying that the infinite lattice model knows something about the CFT, but it's the wrong limit because we are not taking a long distance limit. We're just making the hole small. And that's where my G is, right? So, so this coefficient compensates the disk value, the empty disk. So that's basically the value of the 1 over the value of the empty disk, probably. Right. And so I don't want the 0 boundary. But in a unitary theory for non-zero boundaries, that's not zero. Also, yeah, because the total boundary state depends on that. Then I could have just called this constant, right? I mean, I'm saying there is a constant which makes that work.
Take CR and therefore multiplied by this R. Well, but if you do the Taylor series of CR, that basically
Except for you would have to, right? It has this fractional power, right? But so the leading, so I would say in the unitary case, that's the most singular term. It's like the leading singularity, the coefficient of the leading singularity if you take R. Well, the other terms, so what we are doing is we are expanding. So we have our boundary, which has some gamma boundary state, which lives on some patch of the theory, yes? And then you can expand this in a sum of fields, which sit in the middle, right? So you can expand this as an infinite sum of some fields phi I, which just sit in the middle of this hole with some coefficients. That's called a boundary state. And this expansion expands in the boundary state. And so these coefficients depend on R, right? And so you just filter out the sort of more and more of the boundary state as you do that, I think. But I didn't think about it.
Sorry, before you mentioned some operator delta on the C.
Right. And then I said I will skip it. But now, so where is it here? There's a sort of a delta to the 1 over 6, delta to the 1 over 6, delta to the 1 over 6 here. Right. It's everything goes there, which I don't want. But it's a constant, right? So the delta is a constant. It doesn't depend on the radius. Well, it's a field insertion, but so what the G is the inverse, which I probably should have called it G inverse, of you put this gamma F of delta, and then you just have the empty disk, right? It's the partition function of the empty disk.
check anything about the correlation functions in the lattice form. This state, see that those have to be the same as the CFT.
Well, again, in the limit, yes, right? Because nothing is.
The whole goes to zero.
Yeah. And so we didn't do correlation functions yet, but I would, so there's a natural way to introduce these by modifying these plaquettes with field insertion in the middle, but we didn't investigate those.
Yeah, so just as a broader question, though, is there a natural way to say in the lattice model which operators,
Yes.
which CFT operators correspond to something in lattice?
Yes.
We never-
Well, we can't prove anything, right? So that's.
But at least, I mean, you don't even have to be
So you just put your field you want to measure in the middle of one of these triangles, and that's a new weight. And you insert that weight. Well, what? No. Okay. But you want to do so. I want to insert a field in the middle of this, and you want to use the boundary as an operator. So these are two different ways of implementing operators, which may both work or not work. So I would try this.
What is that? I don't understand what that means in CFT. I was
Okay.
before you boundary CFT is this.
So this is my boundary. Oh, sorry, this is my boundary. Then here I have got states, right? And so this maps to a disk. So this can be unit. So then I glue on these half disks, right? And then here are my boundary fields, kappa I, kappa j. And so I get instead of this weight, I now have a different weight, which is a disk correlator in the CFT with a bulk field insertion in the middle. And these are my new. So I would modify one of these points here to represent a point where an operator is inserted. So I would not do it on the edges. I do it sort of by modifying the weight. And I'm saying it can. Well, it's a 5-point conformal block now. So the answer is yes. But again, it's harder.
This problem of how to identify, even in lattice models where you're 100% sure, I know it gives me the CFT. It's not obvious how to identify local lattice operators with CFT fields.
And we did not investigate this. I would try this, but we didn't even try this in example. So one should sit down, do this in the easing example, and see what you get. Right? So that seems a good thing to try.
CFT construction with defects turned on, and you give it as a two-dimensional partition function.
Mhm.
Is it zero temperature?
Well, it's a statistical model,
Like, obviously,
no temperature. So there's a temperature hiding basic a little bit in.
Oh,
More questions or comments at this point? I have to remember where did I want to go next with this. So now I want to make this model finite. So I'll erase this, leave this for a bit, and then we will switch it off for the example, which I will have a little bit. But we had some questions. Maybe I can go on a little. I'll show you the minimal model expressions if we get there. So the answer is moderately. I can point at that as well. So it's not, I mean, it's a conformal field theory exercise, right? It's a 3-point function, so it's like fixed by conformal symmetry, but you have to be careful what precise operators you need to act on the fields on with, and I'll show you. But first I want to make this finite. So at this point it's sort of pretty. We have control, we have a radius zero limit, produces a CFT. But now we truncate. We fix some H max, some maximal scaling dimension, and then we truncate our bases to those vectors which have scaling dimension less or equal to H max. So the Hilbert space on, so our Hilbert space on an interval with boundary conditions gamma, I truncate the spectrum at H max. That makes it finite, but I lose all control. But now I've got a finite model, and I can formulate a hope, which is that, so this model, now we fix H max, but we still have our parameter R, and we could maybe hope that for H max large enough but fixed, maybe our phase diagram looks a little bit like this. So we have the radius 0 point. They have the radius is d/2, which is when the circles exactly touch. And then maybe the phase diagram looks a little bit like this. So when the circles touch, you get a topological field theory. So you get a 2D TFT. Well, that you can compute what that is, because then only the vacuum state survives here, and you get a TFT. So that's clear. But the hope, which you could formulate, which will turn out to be wrong, and this generality, is that maybe there are some critical points. So we don't know what's happening here, but maybe there are some critical radius, and in this region, we stably recover the CFTC as a universality class. And then over here, maybe we get something else. So that could be a hope you formulate. You started from a CFT, maybe even after a high enough truncation, it recovers in some region the CFT. And this will be wrong in this generality. We'll see it in the Ising example, and then I will make a proposal how to fix it. And then I don't know if that proposal is then a conjecture that works. Okay. Any questions so far? Right, but that's not unitary. So several things fail then.
Okay, yeah, I was going to say, things do go wrong.
Because the vacuum state is now not the invariant state. So, okay, so one has to sit down. I'm not saying it's impossible, but I'm saying I want to do the more vanilla example of the Ising. And that's also interesting. And if, depending on when the chairman actually stops me, I will get to that too. And I will, yeah, sorry. So H, which this one? So it's a conformal field series. So all of these I take to be eigenstates under L0. They have a certain scaling dimension. And I say that this is sort of some number HKI times. So it's the scaling dimension of this field. And I want to only keep fields of a not too high scaling. You can think of it as energy if you want. I don't cut. I don't truncate. Okay? Okay. At precisely this point, the circles touch, and only the vacuum states can propagate through this sort of infinitely thin. So it's the even if you, I mean, so the role of the radius in spirit is a little bit like the truncation, right? So if you make r close to d/2, you also cut off the higher energy states, and exactly at d/2, you get a TFT, and you can. But it's a lattice model, right? So what does that even mean? It could be that there's some region where here it always becomes massive, right? And so it will go to some TFT as ground state theory. I can tell you the answer in the Ising model. But yes, so there will be some region where the theory is massive, and then the TFT is just the ground states of that. It'll be, so the universal behavior will be some conformal field theory, hopefully, but you have to go to long distances to see this. It'll be some, yeah.
You hope to extract some scaling CFT.
I just hope to say the long range behavior is given by that conformal field theory.
Simple enough.
Right. Okay. So that's the hope. The hope will not be quite right, and we will see that in an example. Okay, that question is, I don't. It's. Can you make that more precise? So that point of view is useful in actually computing what all these quantities are, and it may also be very useful to link it to both Paul's models and Frank's tensor network models, but that's something I want to discuss more. So. Okay, so I want to do an example. Where's my example? I want to do the Ising CFT, which is sort of the central charge half, everybody's favorite CFT. I will remind you what it contains just to set my notation, because some people use the wrong notation. So the primary fields are called 1, epsilon, and sigma. And so that's the unit. That's the energy field, which has left-right conformal weight a half, and that's the spin field, which has left-right weight 1/16. Then the corresponding Virasoro algebra at central charge a half has 3 unitary representations. So I'll call the representations of a single copy of the Virasoro algebra, I call R1, R epsilon, R sigma, right? And so, for example, this field lives in R epsilon tensor R epsilon bar. Okay, and then it has topological line defects, so the elementary topological defects. There are 3 of them, the trivial one, and I will use this labeling as well, right? So we know that in these diagonal models, the defects are labeled by representations, and the fusion rules of the defects are sigma is 1 plus epsilon, and epsilon gives the Z2, so epsilon is just 1. Okay, and so now I want to do a little table, possible choices for F. So I write the generators of S, which generate F as direct sums. And so what are the possible fusion subcategories of this? Well, there are 3 of them. One contains just the unit, one is generated by 1 epsilon, and one is generated by everything. Right, so these are my possible choices for F in this example. And those people who stayed for the example in Liang's talk yesterday, so these are also 3 cases Liang discussed. in the context of the Ising model. Okay, so what's the boundary condition? So I want to look at my boundary condition gamma f, which with this delta field, and I want, and so this is gamma hat f, and for the u I just take the Cardi boundary condition for 1. In terms of the lattice model, you may think of this as the all spin up, if you want. Okay. So the boundary condition here, well, if f is just 1, then this gamma doesn't do anything. So here my boundary condition is still labeled by 1. So that's the boundary state. Maybe I should say, so that's the boundary state. And the boundary condition, I call it 1, which in the lattice would be just all spins up. If I do 1 epsilon, then there'll be some prefactor which I'm not writing in the boundary state, but the boundary condition will be 1 plus epsilon. So it'll be a superposition of the Cardi boundary condition 1 and the Cardi boundary condition epsilon, which on the lattice you can think of as having the plus condition disjoint union minus condition. So each configuration, so you average over configurations, but in each configuration the entire boundary is either in plus or in the minus state. Good. And then what happens over here is, of course, you get 1 plus sigma plus epsilon, right? I'm not so there are also this there are also these weights which enter the boundary state. I'm not writing these here. And here, accordingly, you have a superposition of all 3 boundary conditions in the Ising model, plus, free, and minus. Okay. So that's what these are the boundary conditions I would put in this on the circle in my lattice construction. And then I have to compute the state space H with boundary conditions gamma gamma. So this is the state space on an interval where both sides have label gamma. And we right, for example. And here, so there's an interesting thing which we didn't yet have time to think about is what if we do sigma here? Then over here I just get sigma plus sigma, right? But that's also one copy of sigma would be good enough for this. So, so there's some duality thing going on which deserves more thought. Right, sorry, yes. So state spaces. So we know how to compute these state spaces. You just so if you have a minimal in this minimal model, right? So if you have an elementary boundary condition A and another one B here, then the representation. So you get the representation for A tensor B dual, and because it's easy, we can forget the dual, so we can just have to compute the tensor product, and that tells us which representations occur in that state space. So here, I just get H11, the elementary boundary condition 1. If I tensor that, well, that's just R1. So this carries one copy. That's the Virasoro VOA, right? It's its own vacuum representation. Over here, I get 1 plus epsilon on either side of my interval. So I have H11 plus H1 epsilon plus H epsilon 1 plus H epsilon epsilon. And so this becomes R1 plus R epsilon plus R epsilon plus R1. So we get 2 copies of the vacuum representation, 2 copies of the epsilon representation on that state space. And here, well, here it becomes quite big, and I'm not going to write it all down. But again, you write, these should have all been direct sums, but I'm too lazy. So 1 sigma. So you get 9 terms, and for each of these you get some answer. And then if you work this out, you get 3R1 plus 4R sigma plus 3R epsilon exercise. Okay. So these are all internal homes, and so they just are internal homes for so I mean, we're looking at the Ising category as a module category of itself, and then I take this and I look at the internal end of this, for example. Yeah.
Lattice model. Now, how many say the middle example. How
Right.
many states are there?
Well, at the moment, it's all infinite, right? At the moment, because now I'll truncate. That's what I'll do now. But at this point, all these representations are Virasoro modules. They're all infinite. At the moment, infinite, but now we introduce our cutoff, and we just cut off at the lowest non-trivial level to see what happens.
So then the middle, there are 4 states.
And this one will have 4 states.
So
But yeah, we will get there. Sorry, what? Did I get that wrong? What he says. Right, so sigma is 1 plus epsilon, so it should add up to 10. Okay. Or truncate. H max. So I want to choose the smallest non-trivial cutoff. The smallest cutoff is 0. You get a TFT, and I don't want the TFT. I want the next state also included. And then I have to admit here I didn't do this because the next state included would not be a primary state, but it would be the stress tensor, and that would require, I don't think this has been done, so that would require somebody who can do numerics, which is not me. Then here I want to choose the cutoff 1/2, right? So this has 0, this has lowest state 1/2, so if I cut off at 1/2, I get, I keep always the primary state in each of these representations. And so here I've got some choice, but I want to stick with my idea of lowest non-trivial cutoff, and here that would be 1/16. And if I do the cutoff at 1/16, then this goes away altogether, and I just get 7 states on an edge. And here I have 4 states, so 4 states, 7 states. And so this one I will not consider further, but I will, because I don't know what happens, but I can look at this one and this one. And I want to point out one thing, which is I will now not place the degrees of freedom on the edges, but I will go to a model where instead the degrees of freedom sit on the plaquettes. And so let me draw this maybe here. So what I will instead do is I'll go to sort of the dual model, and I place my degrees of freedoms where earlier I had the boundary conditions. And the reason why that's a good idea to do that here is that if I fix what these boundary conditions were, it determines uniquely the state on this edge, right? Because each of these sectors contributes either one or no state, and so by fixing what the 2 sides are, so what these 2 indices are, it determines what is the state which would have otherwise been on the edge. And so in both cases, it makes sense to reformulate the models as a model which has which works on the dual lattice. And I can now try and write the answer for that. So in model 1, so I do this, right? I go to the dual lattice, and so the labels here are those of the sort of non-elementary boundary condition expanded in elementary boundary states. So I've labeled 1 epsilon and 1 epsilon on each of these holes, and I think of this as plus or minus, right? So that starts to look a little bit like the states of an Ising model on a triangular lattice now, right? On each vertex I have plus minus, and then, well, that's the state, they live on vertices. And so I claim, but I'm not going to show you how, that if I compute the partition function of the lattice model, which we constructed out of the Ising CFT, for this cutoff, I get some shift in the ground state energy, so some R-dependent shift to the number of triangles, times the literal Ising model partition function at some inverse temperature beta on a triangular lattice. The literal Ising model. And this is a function of R. And the way, so let's see, so what's the Ising model phase diagram like now? We can say something about this model because we know it for Ising. So we have a beta is, which way around do I need to do this? I want to put infinity here for some reason. So beta infinity is low temperature, right? And then beta is 0 is high temperature. And then we know the Ising model has a critical point somewhere, which is the Ising critical point. And this critical point is unstable, and this region is massive, and this region is massive. So how does it look in terms of the radius? So this function, you can write it down, but it's not very insightful. It just depends on the geometry and so on. Yes, but it's again not, I mean, it's something, right? So I'm saying, but it's, I would think of it as a shift of the ground state energy. It's about.
4 to 2,
right. So I'm saying I labeled my states were originally living on edges, right? And there's 4 of them. But I'm saying they're uniquely determined once I tell you which sector they came from. There's one state which is contributed by boundary 1, boundary 1. One state contributed by boundary 1, boundary epsilon. So the 4 states are the 4 configurations of the spins. And here. And then there's, so then you may wonder, well, does this reach all configurations? But there's also, so this, the configurations on the edges are constrained by the vertex. Some of them are mapped to 0, and so that's precisely, yeah. Goodie. So this will be RSD over 2. So touching holes, so totally, like 0 temperature is also the topological field theory limit of that model. And this has 2 ground states, that also has 2 ground states, good. And then it turns out you cover some range of temperature. So there's some R is 0, and this somewhat random model is, it lands you somewhere, but the important point is that it covers the critical point. So there's some critical radius where you do get the Ising model, right? So that's good. We got the Ising model, but we got it in the wrong way, because this is massive in both directions. And our hope was that there's some region around radius 0 where we stably recover the Ising model. That's not happening here. Okay, goodie. So I want to look at model 2 next. So that's another lattice model we can construct out of the Ising model, but we just preserve a bigger topological symmetry now.
Find that point, of course, is self-duality.
Right.
You can't somehow push down
So that.
defects from the original theory.
List of comments. One is that's Ising specific, that you have the self-duality. So the computation I do over here works for all minimal models in some way, which I can comment on. But in Ising there is a self-duality, and so you can ask, can I use this duality defect somehow on the lattice? And I expect that it walks you between the hexagonal and the triangular lattice. So you have to do slightly more work in this calculation, because you're relating models onto different lattices, or you work with the square lattice. Or
Yeah, so there is a weird duality that takes 6 seconds.
so, but this we didn't work that out. I do not know the answer. That's also on the to-do list. But nobody's working on the to-do list, so it's just on the to-do list.
If you would start with massive CFD.
Right. So you can technically start with a massive model. I wouldn't quite know how to do this. So then you also have to put some boundary condition. Right now, where it's not conformal anymore, right? Because the model is massive, so you've much more freedom, and it might be interesting to look at that too, but we didn't. I don't know. I didn't. So what would, I mean, you could put massive fermions, for example, right? And I don't know what will happen then. I do not. Right. So. Right. Okay. Now I want to do the same thing in model 2. So again here, this model has the property that the two fixing the sector, so the 2 boundary conditions, uniquely determines what the states on the edge would have been. But now now there's one sigma and epsilon, and one sigma and epsilon. And because of our truncation, which I erased, but which I didn't erase, our truncation with 1/16 removed removed part of the state. So it only kept these 7. And what this means is that that the configuration where this is in 1 and this is in epsilon is now 0, because that state is gone. That configuration is forbidden. And so we can write what transitions from one side to the next are allowed. So let me draw my 3 sides, 1 sigma, so my 3 values at each side. And I do have the contribution from the identity. There are 3 of them, and they sort of give these 3 transitions from one value back to itself. And then the other one come from this sigma, and these 4 are going from here to here or back, and going from here to here or back. And so this you may also have seen before. That's an A3 RSOS model. So we get an RSOS model. And that's the thing which continues to work in minimal models. So if I take F to be the fusion ring generated by the 1M cuts label subsymmetry, then I get the AM RSOS model here with this truncation. And so for this model, also known, so you can map that to a loop model, and the phase diagram of the loop model is known. And you get the following. So so there's a sort of a weight per loop, which would be the natural parameter in the loop model. But let me write it like in terms of R. So there's again R is d over 2. Then so here's the thing, which you can shout at me about later. I did not find somebody who told me where the critical points are for the RSOS model on the triangular lattice. Exactly.
Yes.
Okay. But I did find papers which tell me what is the critical point of a loop model on a hexagonal lattice.
Yeah. If that's all the information
Yeah.
you want, that's okay. Yeah. Just forget the phase diagram.
And yeah, so okay, so for the phase diagram, I could have just looked at RSOS. Yeah, so good. So good. So then here we have massive. Then at some point there's a critical point 1. Then there's a critical point 2. And then somewhere over here there's the radius 0. So we don't reach all of the loop model parameters. So this goes on to infinity, but we reach some finite domain here. And so the stability is like this. And this is easing, or at least this is c equals a half. This is 3 easing, or at least it's c equals 7/10. And so now we have a stable region where we get the easing. So this is what we want. And then, okay, there's some other model which you don't care about, but there's now a region around R is 0 where we recover the original CFT. So here it didn't work, and here it worked. Here somehow we had a bigger symmetry, so maybe that's important. And so one can now ask, is there maybe some criterion which can say, why is this one better than that one? And that's what I want to talk about next. Okay. So I'm saying here, so what fails here is that this at this point flows to a massive model, not to the easing CFT. But this one at this point flows to the easing CFT and not to a massive model. And that's what we want. So close to the radius 0, we want to go to the original CFT. That's not the case here. Right. Right. With a caveat, yeah. We will. That's what I want to look at now. In fact, my criterion will walk past the fields which are on the boundary state. Okay.
So the R equals 0 somehow it helps you pointing into the icing.
Yeah, here. So I mean, so you know that if your radius is too big, you're definitely a TFT. And then the hope is that if the radius is small enough, you're the original CFT you started from. So there has to be a transition somewhere, if that picture is correct, right? And so the correct CFT should be sitting close to r equals to 0, if that works at all. I don't know if that's related to what you said. So then, so maybe I can do one more slide. So I want to propose a stability condition. Stability condition. Oh no, that's not the stability condition. That's for Frank. So you can compute what these triangles are, and they are just there's sort of one factor, which is basically an F matrix, and another factor, which is just a conformal 3-point block and doesn't care about the model. So that's what this looks like, and you can compute them. I'm saying you can compute them, but it's just something. So we can discuss what this, right. So that it looks, yeah. And if you sort of restrict your states, and maybe that's also it's the lattice models, you're right, but we didn't make that precise yet. Anyway, so stability condition. So again, we fixed our C and F, and secretly also this boundary condition U, and so there is now a conjecture, or more precise hope, that if you take the boundary state for your cloaking boundary condition with that symmetry, if that does, you expand it right in bulk fields, and if that expansion does not contain any marginal or relevant fields, then there should exist a fixed large enough cutoff and some critical radius, which is positive, so that if your parameter radius sits between 0 and that critical radius, the long-range behavior recovers the original CFT. So that is the more precise conjecture. And I want to check that in the easing example to see that that's indeed at least distinguishes these two cases, and then I want to motivate where this comes from, and then I shut up. Okay. Then what? No. So it could, I mean, I expected if I cut this off at a half, I mean, that's even better. But at this cutoff at a half is not the same model as here, because F is smaller here. Okay.
I was going to ask this cutoff easily compute, but happens if you don't pick it to be the same everywhere. If you wanted to end up with square lattice instead of dividing.
Oh, okay. There's one so I should say we didn't actually compute anything for cutoffs which are not just primaries. So that is something I should have said, but I forgot to say. So we started off building a lattice model which has this topological symmetry exactly, and then we truncated it. And I claim the truncated model still has the topological symmetry exactly. And in fact, it is very flexible in its truncation. On each edge, in each representation, you can keep whatever states you want, and each edge separately, and you still get a model which has this topological symmetry exactly. I mean, you can just start from the square. You can just work out what this model is for the square lattice Ising model. I mean, you could just put that into the construction. I did triangular because I get 3-point blocks and they're easy, but you can also work with easy 4-point blocks. That's not difficult. You can still write those down. Yeah, maybe we can discuss. Okay, so I wanted to do so. Let me do the easing. Okay. Easing. So we had these two cases. 1 plus epsilon was one boundary, and then we had 1 plus epsilon 1 plus sigma plus epsilon was the other boundary. And then for the boundary state, we would also have to include this weight delta, right? Sorry. And then we get two different answers, which I have written down. I think. Right. So for easing, for this one, we get some constant with some square roots of 2 or something, and then you get the boundaries. Maybe I write it like this: the Ishibashi state for 1 plus the Ishibashi state for epsilon, right? And so this has most relevant term 1, but we don't count that as a relevant field, and that contains the field epsilon, and that's a relevant field. So this boundary state for 1 plus epsilon contains a relevant field. Here, your boundary state is just some constant times the vacuum Ishibashi. And so that starts as 1 plus, and then the next term is L minus 2 bar 1. And so this has scaling dimension 4 and is irrelevant. So we see that in this boundary state, there's a relevant operator, and in this boundary state, there is no relevant operator. Okay. So this criterion can at least tell apart these two cases, so that's good. But what's the motivation for it? Okay, does that switch on? No, this one, yes. So what's the motivation behind, or what's the idea behind this condition? The idea is this, and then I'm done. So the idea is that we have, so let's look at a big lattice, size L1, L2, and we have our little circles all have radius r, and they are separated by some d. Let me do this for a square lattice, because now easier. And so now I want to take a continuum limit where I decrease the letting spaces by keeping the overall dimensions fixed. So how does that affect sort of the leading contribution here of terms of the boundary state? So first we have to understand that if we take our gamma f delta and put it at some radius r, the boundary, then this is equal to r acting with L0 plus L0 bar minus c over 6 on this boundary state at radius 1. So the overall singularity we don't care so much about. So let me pull this out. Then there'll be some contribution from the identity, and then there'll be some constant times r to the 2h, maybe I call this 2 delta min, times the most relevant bulk field in this expansion. Right, so the delta is h plus h bar is the scaling dimension. You only have rotationally invariant fields in this boundary state. Okay, so what happens? So now I want to see if I do this for every hole. So then sort of the zr will somehow go like r to the minus c over 6, maybe some constant here, to the number of holes. And then what's the leading term? So let me be a bit schematic here. I get from each hole in here, so I have n holes, say, I get a contribution of, so I get all these ones, and then from each hole I get one of these. So I have r to the delta min phi min. And the positions of these are sort of the n, sort of a sum where these sit. Well, let me write it like this anyway. Where these sit at the places of these holes. And then what is this n? What is the size of the sum? Well, we can compute the number of boundaries, L1, L2 over d squared. Then in this limit where I make the distance small, I want to keep the ratio r over d fixed. So I should sort of pull an r squared out of this. So this quantity is fixed. And then I'm left with r to the delta min minus 2 phi min. And so sort of this maybe indicates that something special is happening as the minimal weight you see here crosses the threshold 2. So if it's relevant, it sort of grows if you make r small, and if it's irrelevant, it shrinks if you make r small. That's my motivation for. So you could also think of this as perturbing a continuum theory by that field as the leading effect of inserting all these holes. And so that's the idea behind the stability condition. And so now it would be fun to test this in examples, but we didn't test it very much. Okay, that's it. Thank you very much.
Problem, you just isolate the identity distribution in the shrinking hole expansion. Here, you say you have n will scale with r, and then up to the power.
Well, so I just pull this out, right? So that's like an overall.
So this is n is the number of.
So it's like a big. So it's a big, right? So this notation really bad. Really, I should have written this. It's like a sum over the whole location phi of x, and there are n whole locations.
Now this became an extra power of r.
And so I'm saying that the number of holes is this size times this size over the area of one of these plaquettes here, d squared. But yeah, and then I make this dimensionless, and so I. I can think of domain walls as boundaries, okay?
And then you did this bubbling construction. What would that look like a domain wall?
So this, which is sometimes called the folding trick, where you have some defect of some nature, you fold it over and you get a boundary of some nature, is more hard to visualize when you have this more complicated geometry here.
Sorry, that's how I'm constructing and you can unfold after. I just mean to say, if you have a domain wall on the CFT, how would that look on the lattice? Would it look like a domain wall?
Well, I mean, there should. So this again is something we didn't investigate, but so the rule of the game is try to write it in the CFT and then put all the holes and see if you can introduce new weights, and you could do this for a boundary, right? So you could, let's do square lattice, I don't know, why not? And so then if you put some other conformal boundary beta, well, then maybe you should try cut it up like this, right? And then you get some sort of boundary weights for the theory, but we did not do that.
So your construction for it not rational.
Right. That's another point I wanted. Okay. Yeah, sorry. Yes? Like, what's your favorite non-rational CFT?
UV.
UV? Liouville. So then again, I don't know what happens, because it was important for me that, so no matter how I truncate, I still get an infinite number of states below this. So I can't make that a finite model in the same way. But maybe if you take one of these boundary conditions which have discrete spectrum, right? So that could be interesting. So you do, right? So in Liouville, you do also have this sort of 1n boundary conditions, right? And I think they have discrete spectrum, right? So one could try that. Yeah, but I don't care about, so this argument would fail, right? So maybe it never gives the Liouville theory back, because there'll always be some relevant operator in there. But right. So for Liouville, I'm saying it does have sort of, yeah. So I don't think there's an easy way to do something with Liouville here. Yeah. Right. But this literal construction would run into some infinities if you try Liouville theory.
In the beginning of the lecture, you showed
Right.
your model has a particle symmetry after the computation.
Yes. So that's not immediately obvious, but it's still true. So even in the truncated model, so you can, I mean, there's two ways to see this. One is to do the actual calculation of factorizing it into disks and just checking that that's still true. But then there is the slightly cheaty argument, which goes like this. So in the untruncated model, we know that if we have the defect here, we can deform it here. Well, it's a conformal defect, so it's transparent to the stress tensor. So I can sort of integrate lots of copies of the stress tensor back and forth on such a link, yes? So far, because it doesn't, the stress tensor doesn't see the defect. But that's like inserting a polynomial in L0. And so I could make this approximate sort of truncation. And so I can build this truncation out of inserting some polynomial in L0 approximately. But this integral doesn't, so this effect, what you do with the defects here, they don't see T insertions because they are topological. So that sounds good, but then if you think about it more, it sort of gets a little bit wobbly because this explodes, and so maybe this explodes faster than it, so there are some issues with this argument, but it's pretty as an argument. Right.
So there's factor, this partition function kind of is not factor, but it's like the given product of wave function and something else. That's why it's a station. But that's I had a question about this actually. Like the Jordan section, how do you see that you will always get something non-chiral at the end?
How do I see that I always get something?
That's one of the big differences.
Well, because this construction wants you to be able to put a boundary, when I define chiral, I would have said that if your CFT does allow for a conformal boundary, the left and right central charge have to be equal for starters. And so you can't, for example, you cannot do in this approach a holomorphic CFT because it doesn't have conformal boundaries. If I do what? If I have a gravitation? Okay, and you're saying there's then a way around. Okay. I see. So you're saying I can't introduce a. Okay. Okay. So say it again more slowly. What? Uh-huh. Right. That is true. Not so clear. Yeah. So we didn't think about that. So I don't see how to cut this then. So then, what does that mean? Maybe that works, but we didn't think about it. Right. So the some linear combination. So I think the most general truncation you can do is you pick a separate, not even truncation, you pick a separate subset of states in each of these representations, and you're allowed to do this for each link separately. That's the most general truncation, I think, which I think one probably can see this with this strange correlator picture, and then this will still preserve the topological symmetry. I'm not sure if you sort of do some mixing what that would do. So Fibonacci would be, say what? So you could run the Liang model, but right. so you have to make f big enough so that it satisfies the stability condition, right? And in minimal models, you can cut out all of these. So if you take the fusion category generated by these cuts labels, and then that's big enough. But I'm not sure if you just take Fibonacci in a minimal model. Yeah, so in the same, there's one epsilon subcategory. But I wanted to point at one other thing. So there was one comment about SU2 level K, the WZW model. So what happens if we do, so can we find an F in this model which satisfies the stability condition? And so if you take F to be just maximal, so F is just all of the topological lines which respect the SU2 symmetry, then it turns out that in this case, always the corresponding boundary state of the cloaking boundary condition is just the Ishibashi vacuum state. But if your theory has weight 1 currents, this still has relevant fields in it. So even though it's just the vacuum, that doesn't satisfy the stability condition if the VOA has currents. So in this model, you can take the VOA V for SU2 level K, and that's rational. And you can show that in fact any rational VOA has a rational sub-VOA with the property that its weight 1 subspace is empty. And you have to work with respect to that one to satisfy the stability condition. So you can't just use your happy SU2 fusion rule topological defects and set up the model for that. This will have marginally relevant fields in the boundary state. So I think that would fail. I think it's just getting massive, right? So generically, you'd expect something massive, maybe. It's like so. This would perturb by you take like a basis of an ON basis of your currents, and you perturb by J bar, and you sum this over all currents. I guess that's just massive, but I don't know. Do you know what the SU2 model flows to if I take the sum of all current dual?
Yeah, well, it depends on the sign. It's either marginally relevant or marginally irrelevant.
Oh, okay. So I see. Okay.
So it doesn't look.
Okay.
Trying to get such construction and the opinions also translated this construction.
Okay. So that's also something we can discuss, which I would be happy to discuss, is that, so the Frobenius algebras, I don't know, they maybe allow you to select different models. So you can do orbifold constructions for this lattice, right? Which would say you start with sort of the diagonal model, and then you put some Frobenius algebra topological defect, and it gives you a different model. I'd probably like to think of this as in the 3D picture, there's a different surface defect you put in the middle of your 3-manifold, which selects different models, and you can expand this in the Frobenius algebra, and we can discuss this later. So I didn't see that talk, so I'm just saying something which may not be related.